This video is to help you complete the magnetism lab. Here I have a stack of 1/2 inch diameter magnets, and I've cut a puck out of some scrap styrofoam. The puck is about 1/2 inch in thickness and about 2 inches in diameter. In the middle I've cut a rectangular slot that will allow me to take one of these magnets and place it into the slot like so, so that its flat faces are vertical. Now remove all other sources of magnetic fields. Those include speakers, headphones, of course the rest of the pack of magnets from the vicinity. Bring yourself a bowl of water like so, and then float your magnet. Another source of magnetic fields may be if you have a steel frame table. In such case you may want to move it away from the table or prop your compass up. So here's my compass, and if I rotate it slightly, we see how it wants to spring back and align in a particular direction. In my case, by looking at a map, I know that this direction here is towards magnetic north, and so the face of the magnet right here is my north face of the magnet. I'm going to use a Sharpie here, carefully pull my magnet out and mark the north and the south poles of my magnet. Now I'm going to take a second magnet and do the same thing to identify the north and south poles of my disc magnets. And here once again I can see that this face here is going to be the north, and in fact, just to make life easier, I'm going to put a north symbol there, so that when I put my magnet back, knowing the orientation, I can determine which way is magnetic north. So now I've identified two magnets and their poles. The next step now is to look at the attraction and repulsion between poles of a magnet. These are my two magnets that had their poles identified using the compass experiment. When I lift them up and I try to put the two north poles together, I see they repel. Similarly, if I put the south poles facing each other, they repel. If I put the north and the south pole towards each other, they attract readily, like so. Using one of our labeled magnets, we can now proceed to label the other magnets. So for example, if I put this on there, I know that the south pole is attracted to the north pole, so this must be the north pole of this magnet. This is the north pole here. Here is the north pole. The north pole is repelling this pole here, so this must also be north. Making this north. This one's also north. And so is this one. Now I have a stack of label magnets. I can go back and I can just label the south poles if they have not been labeled. in the next step, we're going to plot the magnetic field lines. Use some clay to prop the magnet up, like so. And then just put some clay around it so that we can then support a piece of cardboard above it. Like so. Take your cardboard and just put it over the magnet, like so, and press it down onto the clay underneath. Now, using a pack of steel wool, it's best to wear some gloves so that you don't get this all in your hands. Just take one of these and then crumble it over where our magnet is. Let me zoom in so you can see what's going on. We'll see that any of the little metal pieces that fall directly on the magnet are attracted strongly to it. Try and get a good coverage, and then using a pen just tap the board to the side, and we will see the magnetic field line patterns around the magnet will be revealed by the small pieces of iron from the steel wool. Next we are going to make our electromagnet. I've recommended you buy solid core wire, which is available as twisted bell wire from Home Depot. The wire comes as twisted white and red wires. What I would like you to do is to untwist them until you have a 10-foot length of, obviously I've already untwisted that, until you have two 10-foot lengths of separate red and white wire. So you can choose any one from which to make your magnet. You can choose either the white wire or the red wire. We're going to prepare the steel core of our electromagnet. We have a steel bolt. This is the 1/4 inch diameter bolt, 1 inch long. Make sure you get the steel and not the stainless steel bolt, 2 fender washers and a matching nut. What we're going to do, we're going to put one fender washer on like that, put the other one on, and then just screw the bolt on just enough just to hold it on the end. And we're going to wind the wire between the 2 fenders like so. To wind the wire, look at the it's important to have a look at the bolt head. So here I have my nut and here I have my bolt head. So looking at the bolt head, take your wire and leave about 6 inches of tail like so, and then what we're going to do, we're going to wind our wire in a clockwise sense. Okay, I'd like you to make sure that you do get the winding direction correct, so that will allow you to draw some conclusions from the experiments that you do. So we have the wire like so, just bend that to the side, and then we're going to neatly wind the wire as neatly as we can in layers like so. So do this until you've used up all the wire, and make sure you have your about 6 inches or more of wire like so you can make the connections. Once you're done with that, just take some tape, secure the windings, like so, and here we have our electromagnet. What we're going to do, we have to strip the insulation off, so just if you could nick it at some point here, and then you can pull that off. And if you have a look, you will see we will remove the insulation to reveal the copper wire at the center. Do the same on both sides. Just nick it there, pull that off till you've got about a ½ inch of uninsulated section there. At this point also, label the ends of your coil. So here I'm just labeling one end of my wire with the label start, so that I know which end of this wire is the start of the coil and which is at the end, and I know that I've been coiling it clockwise. Set up your compass again, so you may want to mark a north onto your puck and make sure that when you put your magnet in, you align it with the north mark like so, and you can float that magnet again like so. And now we're going to take our electromagnet and we're going to place it so that its axis points towards the center of the bowl. Then you can take a battery like so. So connect it to the ends of the wire, and we will see that when we connect the battery, it will cause our compass to rotate. So let's start by putting the plus of our battery to the start of the coil, and when we connect it like so, we will see the compass turns around. The north pole is facing the bolt head, indicating that the bolt head is the south pole, has a magnetization such that it's the south pole. If I reverse the battery now and make the same connections, I will see now that the south pole connects to the I will see now that the south pole is now attracted to the electromagnet head, bolt head. Don't leave your battery connected too long, otherwise you'll deplete your battery. You may be able to pick up some paper clips with your electromagnet. We attach it like so, and you can see here I'm able to pick up paper clips with my electromagnets, and when I release the current, the electromagnets fall away as the electromagnet is not energized anymore. The next thing we are going to do is to explore electromagnetic induction. To do that, we're going to take our multimeter and put it into the millivolt mode. So turn the dial until it's onto 200 millivolts. Put your red lead into the volts, ohms, milliamps socket, and your black lead into the COM common socket. Next, we'll take the lead like so, and we will bend it around. So, and then squeeze the end of this quite tight so that when we put the probe in, it will start to rub against the uninsulated wire and make a good connection. So put your red lead to the start of the coil, and then similarly for your black lead, do the same. Just bend that in a little bit so that when I put this through, it scrapes against it. Now you've done that, just to double check that it actually is making electrical connection, switch your your multimeter onto the ohms setting. So here I've got it onto the 200 ohms. I'm going to turn it on. We see here that it's giving a reading of 1 ohm. That's a good result, showing we've got a good connection. I'm just going to simulate what happens if there isn't a good connection by unplugging this lead, and you will see here the meter indicates an out of range condition, indicating that the resistance between the leads is high, and hence probably not connected. If you have that situation, you may need to adjust your connections here until you've got a low resistance between the probes. Once you've got that, switch it back into the 200 milliamp range right here, and that's the most sensitive millivolt setting for this multimeter. Now we have our electromagnet connected to the multimeter and we're measuring millivolts. I'm going to take the north end of my magnet and I'm going to move it close to the head of the bolt, and we can see when I move it in, when I move the north pole in, we do get a brief increase in voltage. When I pull this away, we get a voltage reading, but it's negative. We get the opposite effect if I use the south pole facing towards the bolt head. Notice that if we leave the magnet stuck on the coil, no voltage is induced. Similarly, if we have the magnet removed from the coil, we have no induced voltage. We only have an induced voltage when the coil sees a change in the magnetic field that it is exposed to. And that's the end of the lab.